When we want to weigh something here on Earth, we can just put it on a scale. Or if you're a frequent enough flyer, you can just go, yeah, that's about 40.3, I'm good. But that only works for things you can hold. What if you wanted to weigh the Earth itself? Well, lucky for you and the scientists who would find such a measurement useful, we have multiple techniques to weigh not just the Earth, but any other planet. I see all you commenters about to type, mass isn't weight. Don't worry, we'll get to that. Behold, your standard bathroom scale. On the inside, it has a set of springs, and when you or your suitcase stands on it, or you and your suitcase because you're about to do a clever bit of subtraction, those springs get squished. By knowing exactly how squishy those springs are and measuring how much they move, the scale can measure the force of your body pressing down on them. That means that if you stood on a scale on, say, Mars, you wouldn't weigh the same as you do on Earth. The springs wouldn't get squished as much. But while we often think of weight as a measure of some kind of size, it's actually the gravitational pull exerted on a given mass. Mass is an intrinsic property of a thing. Just like a person could say, I have long ebony black hair with purple streaks and red tips, they can also say, I have 60 kilograms of mass. However, I don't think anyone but the most pedantic of scientists would say that, as opposed to, I weigh 60 kilograms. All this is to say, you can't really weigh the Earth, even if that's the term we use colloquially. For a planet hanging in the near emptiness of space, a weight means nothing. But scientists have wanted to know the Earth's mass for centuries. In the 1700s, scientists devised a way of estimating Earth's mass by measuring the gravitational pull of a huge mountain. This was first attempted in the 1730s at the Chimborazo volcano in modern-day Ecuador. Because Earth bulges out of the equator, the peak of this thing is actually the farthest you can get from the center of the Earth while wandering around on its surface. But the first successful measurement was in 1774, half a world away on the Scottish mountain Schiehallion. And their tool of choice, a hanging plumbob, basically a very precise weight on a string. If you're near a big mountain, which itself has a lot of mass, the plumbob won't point straight down towards the center of the Earth. Instead, it's deflected a bit, drawn by the gravity of the mountain. This is known as the deflection angle. There are other things about a mountain that scientists can measure pretty easily: its volume, its height, and the density of its rocks. So scientists use that deflection angle to compare the gravity of the mountain, which relates to its density and size, to the gravity of the whole planet. And since they had a pretty good idea of the radius and volume of the Earth, they ended their calculations with an estimate of the planet's average density. According to their numbers, Earth was about 4 or 5 times as dense as if it were all composed of water. Modern measurements show the correct figure is about 5.5 times, thanks to our planet's molten rocky interior and iron core being super dense. But it was close enough for a couple decades. Then in 1798, there was the Cavendish experiment. This guy, Henry Cavendish, measured the gravitational attraction between some carefully suspended balls, and from that got the mean density of the Earth. He calculated it to be 5.48 times as dense as water, only about 1% off from the value we know today. Modified versions of that experiment also helped us measure a super fundamental value in physics known as G, the gravitational constant in Newton's famous law of universal gravitation. And thanks to G, plus some physics equations from another old-timey scientist, Johannes Kepler, we don't have to land a robot on other planets and rerun the Cavendish experiment to weigh each of them. Instead, we can just do some clever math. By combining Newtonian gravity and Kepler's laws of planetary motion, we know the orbits of things in space directly relate to mass. For example, Mars has 2 little space potato moons called Phobos and Deimos. So by measuring how fast they orbit Mars, we can get the mass of Mars. If these little guys orbited faster, we'd know that the thing they were orbiting had to be more massive, and vice versa. Modern technology also allows us to get a much better sense of a planet's gravitational pull. For example, the Juno spacecraft that NASA sent to Jupiter was designed to measure Jupiter's gravity every time it swung around the giant planet. As Juno orbits Jupiter, it sends signals to Earth, allowing us to measure its orbit incredibly precisely. And just like with Mars's potato moons, astronomers can use that info to calculate Jupiter's mass. In the 1700s, we were hand-waving around numbers like, Earth is 4 to 5 times as dense as water. But now we can say with great confidence that Jupiter is 317.828 times Earth's mass. It might sound a little weird or perhaps unnecessary, but knowing Jupiter's mass specifically is really useful for other bits of astronomy. It is, after all, the most massive planet in our solar system by a lot. For example, in a paper published in 2023, astronomers used Jupiter's super precise mass to calibrate their measurements and discover the faint noise of a gravitational wave that's permeating all of space. But just like that impressive science project, we need funding. So here's a quick ad.
Thanks for watching SciShow and supporting our long-running series like the Rocks Box. Every month, Rocks Box subscribers get a mineral or fossil sample delivered right to their door. In your Rocks Box, you can expect everything from fool's gold to emeralds to trilobites. And to enjoy those treasures to the max, you can grab a SciShow Jeweler's Loop, too. This has been a very popular subscription, and so we've had a waitlist for a while, but right now we have spots open. So if you've been hoping to get your very own Rocks Box, now's the time. Find the monthly Rocks Box subscription, individual samples, and Rocksbox merch at complexly.store/rocks.
It's not just planets in our own solar system we can weigh now. Since the 1990s, we've been studying planets around other stars besides our sun, better known as exoplanets. There are lots of methods for detecting exoplanets, and they each come with different ways of getting to the exoplanet size. With the transit method, where we see how much of a star's light a little planet blocks out, we can only get the radius, not really the mass. So we'll skip right over that one. Next, we have direct imaging, where we're directly taking a picture of an exoplanet. And with this technique, we can sort of measure mass, as long as you make some assumptions. These photos show how bright an exoplanet is. And brightness depends on how big the planet is, how far away it is, and how old it is, since planets get fainter as they age and cool off. So you can estimate mass from these kind of observations, but the accuracy depends on the models scientists make and how well they've estimated other properties. But there are two methods where we really can measure an exoplanet's mass. The radial velocity method and astrometry method both measure how much a star moves in response to a planet's gravitational tug. How much the star moves depends on how massive the planet is. Bigger planet, bigger movement. Okay, you also have to know the star's mass and how far away the two are from each other, but astronomers have gotten really good at estimating stellar masses, and they can get the distance from how often the signal they're detecting repeats. Thanks to all these methods, astronomers can measure the masses of planets in our solar system and planets around other stars. But what about a planet that isn't actually around a star at all? Planets that don't orbit a star are called rogue planets, or free-floating planets, or if you want to get really fancy, isolated planetary mass objects. Some of the larger rogue planets may have formed all on their own out in the middle of nowhere, but most were probably made around a star and then kicked out of their home system by another big planet's gravity. Put them all together, and there might be even more of them in the galaxy than your traditional planets that do live around stars. There's one more exoplanet hunting technique that's particularly good for finding these nomad worlds. It's called gravitational microlensing. We know that mass bends the fabric of space-time. The more mass you've got, the more you bend it. And if light from an object passes by something massive, that light will get focused and brightened as if it's passed through the lens of a magnifying glass. In the case of planets, be they rogue or regular, they're magnifying light a lot less than an entire galaxy. thus the term microlensing. Now, because we're dealing with magnification and brightness, it's critical to know the lens's distance before we estimate its mass. And rogue planets, being small, dim worlds in the depths of nothingness, are notoriously hard to get distances for. Enter another one of astronomy's classic techniques: parallax. This is the idea that an object will appear to move places if an observer looks from different spots. It's like holding your thumb out in front of you and looking with just one eye, then the other. You'll see your finger looks like it's shifting back and forth. Note, this is easier if you can actually close each eye independently from one another. So if you're having trouble, you might need to use your free hand to close an eye that can't. Traditionally, parallax is measured when Earth is at different spots in its orbit around the sun. But in a paper published in early 2026, a team of astronomers got the first official mass measurement for a free-floating planet using something more like the thumb trick. They examined one of this planet's microlensing events using telescopes on Earth and the Gaia satellite in space. Same time, different place, instead of different time and different place like usual. Well, not the exact same time, because the two detectors weren't the exact same distance from the light source, but for our purposes, close enough. In the end, the parallax measurements produced a distance of almost 10,000 light years from the center of the Milky Way. And with that knowledge, the lensing event suggested the planet was about 22% the mass of Jupiter. That's roughly similar to the size of Saturn, which means it probably didn't form in the void and was instead booted out from its original home. This measurement is probably the first of many more like it, especially with NASA's Roman Space Telescope launching as early as fall 2026. It's going to be an absolute microlensing machine. Scientists expect it will find at least 1,400 more planets with microlensing, which is a lot considering we still only know of about 6,000 exoplanets using all our techniques combined. And when we finally find one worth visiting, you can use your handy-dandy bathroom scale to make sure your suitcase is under the weight limit.